after lecture. Is that good? Yeah, yeah, okay. All right, so we are talking about chapter 8, I think, for us. And we've been talking about gases, and we got into a bunch of gas laws last time. So we talked about some important units associated with gases. For us, in most chemistry classes, there's sort of the big three, which is atmospheres, torr, and millimeters of mercury. So those are sort of the big three units that we'd see. Again, there are other units like, again, PSI, bar, kilopascals, and so forth. But I would say most of the time we are going to deal with probably these three types of units. The 760 is an important conversion factor. It allows you to go from atmospheres to either torr or millimeters of mercury. If you were going to do that, you would be multiplying by the 760. And if you have millimeters of mercury or torr and you want an atmosphere, you would be dividing by the 760. And a reminder as well that torr and a millimeter of mercury are pretty much a 1-to-1 conversion between those two. So if you need to convert between those, you pretty much just change the units. The numbers stay the same. We talked about some gas laws here. Remember, most gas laws deal with pretty much these three variables: pressure, volume, or temperature. We started with, I think, our friend Boyle. He did a little P1 V1 equals P2 V2 action. And he looked at pressure and volume relationship, and he held constant here temperature in these situations. And what Boyle saw was, as we talked about, as the volume increases, the pressure goes down, and vice versa there. As the volume goes down, the pressure will go up. So pretty much in a much smaller volume, the gas molecules have less room to fly around in, which means they will have more collisions. More collisions will result in a higher pressure, as opposed to if the volume gets larger, much more room for everybody to fly around in. That will decrease the number of collisions, and we would see the pressure start to come down in that case. So basically, as one goes up, the other goes down. We also saw Charles' law, which is V1 T1 is equal to V2 T2. This is at constant pressure. And with that, we talked about Gay-Lussac's law, which is P1 T1 is equal to P2 T2. And that is at constant volume. Now, in each of these situations, because of what is being held constant, different things occur. When we talk about our constant volume, which means that it is fixed and rigid, when we increase the temperature, our gas molecules will start to fly around faster, as we talked about. Because the volume is fixed, it's not going to go anywhere. That is definitely going to lead to a lot more collisions occurring. And what we will see is an increase in the pressure that will occur in that case. Obviously, vice versa, if we lower the temperature, our gas molecules will be flying around a lot slower. They will still be in that sort of fixed volume of space, which means the number of collisions will come down, and we will see the pressure come down in that case. So the relationship we see there is basically as one goes up, the other goes up, and as one goes down, the other goes down. Now, when we talk about sort of Charles' law here with our constant pressure, really what happens in Charles' law situation is, in order to maintain that constant pressure, it is actually the volume that adjusts to allow the pressure to remain constant. So as we increase our temperature, much like we saw there on the right, we will have gas molecules flying around a lot faster. But in this particular case, the volume will actually adjust and become larger. And as the volume becomes larger, it gives everybody more room to fly around in. And what that essentially does is keep the number of collisions relatively constant, and thus the pressure is able to remain constant, even though they're flying around faster in this situation. So to keep that pressure constant, we will see the volume adjust accordingly with the temperature here. And as the temperature goes down, the opposite's going to happen. Once again, our gas molecules will be flying around slower, which would normally lead to a lowering of the pressure. But what happens here is the volume actually adjusts down smaller, and that creates the same amount of collisions occurring, even with our slower moving gas molecules. and we will see that the volume basically will come down with it. So the way it's able to, again, sort of maintain that constant pressure here is the volume's able to adjust to allow the number of collisions to remain the same. We also talked about, I think, our friend Avogadro and his law. Avogadro is at constant temperature and pressure. We get a V1 over N1 is equal to V2 over N2. And remember that in this case, N is the moles and V is the volume. Also, obviously, up here, as we talked about, most important as well, what they saw when they looked at that graph, as we talked about, is essentially everybody hits that minus 273.15 degrees Celsius, which, as we talked about, if it is a gas law, temperature always needs to be in Kelvin, obviously up there for those guys in each of these cases. The relationship here with Avogadro's law is basically the volume and the number of moles are pretty much the same, proportional to each other. So as the volume increases, so does the number of moles. The sort of practical application of this was that we saw if you had an equation where everybody was gases, you could kind of do a stoichiometry problem by looking at these like we would normally do a mole to mole relationship, like 2 moles of A is equal to 3 moles of B. We could actually do a volume to volume relationship if this is, again, under constant temperature and pressure conditions. We could say, for example, 2 liters of A would give us 3 liters of B. The benefit of that is when you're doing stoichiometry involving gases, it can allow you to sort of skip using the gas law in the problem, and you could go right into sort of the stoichiometry part, but it does need to be all gases, and it does need to be under temperature and pressure being constant in that condition. Putting all those guys together, as we talked about there, gives us the ideal gas law, which is PV equals nRT. And remember that the ideal gas law obviously is different than all the other ones that we see up there. There is no like before and after situation. It is sort of a 1 pressure, 1 volume, 1 temperature situation. It is also the most restrictive in terms of units. Pressure here needs to be in atmospheres. Volume needs to be in liters. N should be in moles. And T should be in Kelvin. And once again, really the reason for all that is the gas constant, which you always have available to you, which is 0.08206. It has pretty much all those units, liters times atmosphere, divided by Kelvin times mole. Once again, we talked about you could also, and a lot of people do use sort of a rounded version of that number of 0.0821. Lastly, I think we also talked about the relationship known as STP. STP is standard temperature and pressure. And when somebody says STP, they are really giving you some values there. So STP, right over here. STP is a temperature that is 273 Kelvin, and the pressure basically is 1 atmosphere. So in a problem, obviously, if they state STP, those are the 2 values that you should use. You can obviously, even at STP conditions or non-STP conditions, you could always go into the ideal gas law and sort of solve a problem. But if you happen to be at STP conditions, which I think like the last example we did last time, if you are at that STP conditions, you can sort of avoid the ideal gas law and use this conversion that 1 mole of any gas basically will be 22.414 liters. So once again, that is sort of a conversion that you can use under STP conditions, and obviously it needs to be STP conditions to use that. Otherwise, you should use the ideal gas law probably in that case. And once again, you can use the ideal gas law regardless in that case. Any questions on the gas stuff that we talked about there? Yeah. To convert to Kelvin, is that what you're asking? Yeah, to convert to Kelvin, the temperature in Kelvin would be temperature in Celsius plus a 273. Yeah. You I guess potentially you could, but usually not too often. But just to remind, if you needed to go from there, temperature in Fahrenheit is 1.8, temperature in Celsius plus a 32. And that means that the temperature in Celsius would be temperature in Fahrenheit minus 32 divided by 1.8. So if you happen to have Fahrenheit, you would probably need to go this route and then into that route there. Yeah. I would probably think most of the time it's going to be in Celsius. Is pretty much, you don't really see too much Fahrenheit outside of usually like the chapter where they talk about temperature conversions, usually in chemistry, but potentially I guess you could. Other questions? Okay. So let us continue on. Let's talk about another sort of gas law. And this is a gas law that basically takes into account all of the sort of factors, if you will. So if we take the ideal gas law and basically solve for R, which is the gas constant, we can actually set these two guys equal to each other, which is what we see here. And in most cases, if you don't open up the lid there on the gas container, the number of moles of gas will pretty much remain constant as well. So this oftentimes will reduce down to is sometimes referred to as the combined gas law. And that is basically P1 V1 over T1 is equal to P2 V2 over T2. So these are our normal sort of players here. The pressure on both sides, again, could be any unit as long as they are the same. Volume could be any unit. Once again, temperature does need to be in Kelvin. I think we talked about it last time as well. Pretty much any gas law, put it in Kelvin. Again, even on questions where they give it to you in Celsius and want the answer in Celsius, you still need to put it into Kelvin when you go into the gas law. This is the one that gives people sometimes trouble rearranging, a lot going on there, but you can solve for obviously any of these type of conditions. This one also is a really good one just to remember because frankly, from this one, you pretty much get all the other gas laws if you needed them. So if you wanted to choose maybe one or two to remember, I would go with this one. And just to show you how that works, if you remember this gas law, which is the combined gas law, and you are reading a problem and you see it has no temperature, you just scratch out temperature and you have Boyle's law. If you remember this gas law and you're going through a problem and frankly it has no pressures, you scratch out pressures and there's Charles' law right there. And if you're doing a problem and you go through it and volume is not there or held constant, you scratch out that and you got Guy-Lussac's law. So really from that one, you scratch out the thing that's not there or being held constant, and you pretty much have all the other gas laws that you need. So if you're going to invest your time to memorize PV equals nRT and this guy, and you pretty much should be able to get any gas law that you would need to use in most cases, except for maybe Avogadro's law. But other than that, you could probably get Avogadro's law if you put the N into this one as well. Any questions on how to do that there? You cross out the thing that's either held constant or not in the problem. You get there. And if you want to do the advanced version here, you could leave the N in there like we saw on the last slide, and you could even get Avogadro's law from it. So in this case, if we were doing some type of Avogadro's law, pressure would be constant and temperature would be constant. And now I have Avogadro's law as well. So if you want to leave the N in there as well, you will just have to scratch out the N on a lot of them, but you'll get to everybody as well. So that's a good one to remember. It can really get you all the other gas laws without having to individually remember all the gas laws. Any questions on that there? All right, so let's try our rearranging skills here. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97 atmospheres. Pressure goes to 8.25 and we heat it to 125. We're looking for a new volume here. So take a couple minutes to see what you come with. Okay, let's take a look. So as we talked about last time, it's a good idea just to kind of pull out the information here. So we got a temperature that's 27 degrees Celsius. It goes with a volume that is 9.55 liters and a pressure here that is coming in at 2.97 atmospheres. We're going to change our pressure to 8.25, and our volume is what we are looking for, and we will have a final temperature of 125. So again, you could kind of see the combined gas law here as we got everybody coming out here, our pressure, our temperature, and our volume. In terms of our pressure, we're good because the units are the same on both sides. But like normal here, we do need to add a 273 here to each of these to convert these guys into Kelvin. That should give me 300 Kelvin. I believe that should give me a 398 Kelvin. So this is a P1 V1 T1 equals P2 V2 T2. In this case, we actually want to solve for V2. As we talked about, the quick way to rearrange these is as you go across the equal sign, everybody ends up in the opposite location. So this guy is going to end up on top, and the P2 will end up on the bottom. And that will give us P1 V1 T2 divided by T1 P2 is equal to V2. Again, just kind of moving those guys to the opposite sides. We're basically multiplying and dividing them over to the other side. At this point, we want to make sure we get everybody in sort of the right spot there. So we're going with P1 up on top, which should be 2.97. We got our V1, which is 9.55 liters. And here it is our T2 that should be up on top, 398. Divided by our T1 on the bottom, which is 300. And lastly here, our P2, which is 8.25 atmospheres. Atmospheres will cancel, Kelvin will cancel, going to leave us liters as the only unit that's left, which is kind of good since that is a volume. So we're going to take our 2.97 times it by 9.55 and times it by 398. We're then going to divide it by 300, hit equals, and divide it by an 8.25. Going to give us a, we'll call it 4.56 here in terms of our volume. That will be in liters. Any questions on that one there? So I'd say this one, sometimes gives people a really hard time doing the rearranging. So if that's a problem for you, you should take some time to make sure you know how to, again, properly sort of rearrange these guys. Any questions on the combined gas law here? Yeah, I would think so. Questions? All right, so next couple of things we're going to talk about is maybe some calculations that you might not have seen yet in terms of gases. We're going to talk about sort of calculating the density and also the molar mass of a gas. So to calculate the density, which is mass over volume here, for a gas, we take basically the pressure in atmospheres, our gas constant, and our temperature in Kelvin, and that is the molar mass, which is grams per mole in this case. The molar mass, which is usually in units of grams per mole, can be solved by taking the density, which will be in grams per liter, times the gas constant, our temperature in Kelvin, times our pressure. So these are a couple of sort of formulas here that you could remember, but you really don't need to. For example, these are really both sort of based off of PV equals nRT. So you could really sort of derive both of these equations, or I guess a better way of saying it, you could solve for both of these things, density and molar mass, by simply using really the ideal gas law and the conversion. And basically it's the same thing that these formulas do for you. Remember, as we talked about earlier, when we do calculate density, it is basically grams per liter typically for gases. So why don't we try one here, and then I'll show you sort of how it works with the ideal gas law. So why don't you give this a try first. We have a 2.1 liter vessel, contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass here of this compound? These formulas are, to be truthfully honest with you, I don't know them by heart. And that's because, again, I'm only choosing to remember the ideal gas law because I like that one, along with the combined gas law. It feels like two really good ones. And again, if you can't remember those formulas we just saw, you really, again, can use the ideal gas law in both of those situations and sort of treat it as a conversion problem, and you could get yourself there. So with that being said, we're looking for the molar mass. We obviously have the volume given to us, which is 2.1 liters. We have the mass, which is 4.65 grams. We have a pressure, which is 1 atmosphere. And we have temperature, which is 27 degrees Celsius. Are looking for molar mass, which is grams per mole. Frankly, I don't need to do much there. I already have the top number, so that's all I need to worry about there. That means really all I need to figure out is moles, and that would be this guy right here in our ideal gas law. We have the pressure given to us, we have the volume, we have the temperature, and we always have R. So here I'm just going to use the ideal gas law and solve for N, which would be PV over RT. Obviously, we need to make sure everybody's in the proper units. So we'll convert our temperature here into Kelvin. And that's 27 plus a 273. There we go. So N in this case would be our pressure of 1 atmosphere, our volume of 2.1 liters divided by our R, 0.08206 Kelvin mole, and our temperature of 300 Kelvin. And if I do all that good stuff, 1 times 2.10 divided by 0.08206 and divided by 300 gives me moles of 0.085303. And that, frankly, is the bottom part that I need. And all is left is just to divide those two numbers, and that will be good. So my molar mass in this case would be my grams, which was given to us, divided by the moles I calculated from the ideal gas law. And that will give me 4.65 divided by that number, about 54.5 grams per mole. Any questions on that? So again, another situation where, frankly, you don't need to learn another sort of formula. You could just work it off of the ideal gas law and figure it. Although if you do like formulas, you can remember it and just work it off of that formula. They both should get you to the same place, but less memory this way, I suppose. Yeah. Any questions on that one there? What was that? Yeah, that's basically what molar mass is, grams per mole. So since they already gave me the grams, I got it. So really the only thing I needed was to get the moles. And that's really, in this particular case down here, that's basically what we did here by dividing by the moles, which is really the ideal gas law part here. That's why it's flipped around, and the density there. But again, I think it's a little straightforward if you kind of take it with this approach. But you can do it either way. They both should obviously give you the same answer. Any questions on that there? All right, let's try one with the density perhaps. What is the density in grams per liter of oxygen gas at 778 torr and 27.5 degrees Celsius? Oxygen is obviously 16 there on the periodic table in case you need it. I will. And once again, you could go with the formula that's over there. But once again, I'm going to opt to use my ideal gas law because, frankly, I have vested in learning only 2 gas laws this whole time. So I'm going to go with this one and do more of a conversion type factor. So we are looking for density in grams per liter in this case. In this case, we are given the pressure, which is 778 torr, which, since I'm going to use ideal gas law, I probably should convert. So why don't we just do that while we're here? And we'll convert that into atmospheres because it needs to be that way when we go into the ideal gas law. Which, by the way, if you use the other formula, it needs to be in atmospheres as well because it frankly is based off of the ideal gas law. So you got to get them into atmospheres. Here, we also have the temperature, which in any gas law will definitely need to also be converted into Kelvin. So we'll do that as well. So we got a 27.5 plus a 273, going to give us 305 Kelvin. So at this point, that's pretty much all the information I got. So if I check off my boxes here, I do have the pressure. I always have R and I do have T. So what I'm going to actually do in this case is solve for N over V. And N over V will equal basically P over RT when I solve for it from the ideal gas law. By the way, N is what? Moles. V is liters. That's also the molarity, by the way, of the gas right there, moles per liter. So if you solve the ideal gas law for N over V, you basically just got the concentration of your gas and molarity. That's okay, because if I eventually want to get to here, which is liters on the bottom, and my liters are on the bottom, so that's good, which means I just need to convert grams into moles, and that is what the molar mass is for, right? Because molar mass is grams per mole, which in this case would be O2. So that would be 2 times 16, right? Would give us 32 grams per mole. So if we put our gas information into here, we will take our pressure, which has been converted to the proper units. We'll use our gas constant, which obviously is always the same number. And we'll take our temperature, which we also converted to Kelvin. In this case, atmospheres will cancel, Kelvin will cancel. It's liters over mole, but when we do the division, it becomes moles over liters, right? When we flip it. And that will get us 1.024 divided by 0.08206 divided by 300.5. Gets us something like 0.04153 moles per liter. And once again, pretty much I got the bottom part. I just need to convert the top part from grams to moles to grams. And again, that is where the molar mass comes into play. We'll just do a little dimensional analysis. 32 grams per mole. Moles will cancel. And now we will have the units that we need, which would get us 1.33, we'll call it, grams per liter. So once again, that other formula really is this equation, because if you look at the other formula, it is this equation times the molar mass, right? That is what we just did, basically. So again, you can remember those other formulas if you like, or you could just roll with the ideal gas law in pretty much all situations of density or molar mass, and just kind of treat it almost like a conversion sort of problem, and you could get there. Yeah. What is torr? Torr is a unit of pressure. It's equivalent to basically a millimeter of mercury. It was really named after the guy who invented the barometer. His name was Torricelli, so they called it a torr, which is equivalent to a millimeter of mercury. They're a 1-to-1 conversion. Other question? Yeah. Yeah, so in this case, you got basically 2 unknowns, basically, right? So you got to kind of isolate your unknowns there on one side. So you could have flipped it around, just your units would be backwards. So if you think about the units of where you want to end up and where you want to start with, that's why I did N over V rather than like V over N. You could do it that way, but at some point you got to flip it back around the other way to get the units in the right spot. Yeah. Other questions? Okay. Fun with gases. To be continued.